Hello, so in this video we're going to start moving on to looking at these things called linear systems of ODEs. Now they sound quite nasty, but trust me, they're really not. And in this video it's going to be all this video is going to be about is just pretty much trying to form these ODE systems. So basically what you'll end up is a system is, if you like, just a group, I suppose, of ODEs. Okay, so this is an example. I'm just going to consider the two-dimensional case. So dx by dt and dy by dt. Okay, and this is a linear system case. So I'll come on to that in a minute. But basically, what does this mean? Dx by dt and dy by dt. Well, I've got two variables. Okay, I've got x and y. All right, and I've got, basically, I'll end up with a description of how each variable changes with respect to time. This is all this means. So this dx by dt means that it tells me how x changes with respect to time. And dy by dt tells me how y changes with respect to time. Now there's special notation for that. Whenever we differentiate something with respect to time, to see how something changes over time, physicists kind of beat us to it, but we mathematicians kind of steal it from the physicists. So the mathematician's way of writing it is dx by dt, but just for convenience, we tend to write it with a dot. Because physicists, as you can imagine, deal with systems that change over time all the time, if you pardon the pun, right? But they deal with these kind of systems all the time, so variables that change over time. So whenever something changes over time, we just give it the equation y dot. I don't know why I'm drawing a vector underneath it. But yeah, this is x dot and this is y dot, okay? So this is how my x variable changes with respect to time, and this is how my y variable changes with respect to time. Well, I want to consider now a very special case, which is when my x variable changes over time, all right? But it's described by a linear function. So in other words, it's described by a linear function, so it's of the form ax plus by plus some constant k1. Okay, and the same thing for y. I'm going to have this time a different constant, cx plus dy plus k2. So all I'm just basically doing is saying these are two linear functions, and obviously distinguishing the two, I should say. Differentiating is the right word, but not in this context. So distinguishing the two, I'm just going to use different constants and coefficients. Okay, so basically this is a system of a linear system of ODEs. So it's just describing how each variable changes with respect to time. And I'm going to suppose that the right hand side is a linear function. So how my function changes over time is described by a linear function. We'll come on in a little while, not in this video, but a few videos down the line, of looking when this right hand side isn't linear, when it's actually non-linear, and actually you'll realise that there's, in certain cases, we can actually consider a non-linear case as a linear case, okay? But that's all to come. You've got all that to look forward to. All right, okay, so I should also say this word autonomous now. I'll introduce this word autonomous. Autonomous. And the reverse of that, or the opposite of that, if you like, is non-autonomous. Okay, so we've got autonomous and we've got non-autonomous. These equations at the moment are what are known as autonomous. Okay, what does that mean? Well, think of the word automatic. Okay, it means by itself. All right, it means something happens by itself. So if these equations are describing how a variable changes over time. Well, if this right-hand side has got a t in, so in other words, it's got a time variable in, then it's non-autonomous. Because in other words, it's not happening by itself. It's dependent on whatever that value of t is at that time. So you've got to actually plug in a value of t. If this has a t in it on the right hand side, you've got to actually plug in a value of t. So in other words, it depends on time. Whereas if it hasn't got a value of t in, okay, so these equations haven't got a value of t in, then it means that it's autonomous. It means it happens by itself. It doesn't matter what time you're at. Okay, it's not dependent on what time it has to tell me. It's a bit like it's a bit like somebody who's running by a schedule. That would be something that's described as non-autonomous, because they'll think, right, okay, what's the time? Oh, that means I've got to do something. So, oh, it's 3 o'clock. That means that I've got to go and put the bins out. Or, oh, it's 10 o'clock. That means I've got to go and make dinner. That would be the description of a non-autonomous system, because you're dependent on what the time is. Whereas an autonomous system just means that something happens regardless of what time it is. So the time, yeah, I think I made that point clear. It basically hasn't got a time variable on the right-hand side. So this is described as autonomous. Okay. Okay, so basically I've got this system. Now in general we can have n different variables. I just consider the two-dimensional case. Why the two-dimensional case? Well, it's the simplest case. Okay, the two-dimensional case is fairly obviously the simplest case because you just got x and you just got y. Okay, but you can't just consider one variable because because of where we want to end up. We basically want to try and combine these two equations together into one equation to kind of get a description of how the variables interact with each other over time. That's what we're looking for, how the variables interact over time. All right, so basically we want to try and combine these two things together. And obviously if we've only got one variable, then it's just interacting with itself, so it's not actually telling us anything interesting. Okay, so two variables is the simplest case. In general, like I say, we can consider n different cases, but the thing is, if you can get the two-dimensional case in your head, then the n-dimensional case just follows on from that. So however many variables you've got follows on from that. So okay, what I want to basically do is try and take this equation, these sets of equations, okay, these two equations here, two systems, and combine them into one equation, okay, because I want to kind of deal with them together. I want to see how they interact with each other over time. So I want to try and put them together. So what I'm going to do, okay, I'm going to end up with something dt. I'm going to work out what that something is first of all, or what that something is. So basically, the first things first, I want to create a list of all my variables. So my variables are x and y. So I've got a list of my variables, okay. Well, are you happy that I can just form that as a vector? Yeah, because that is just all my variables. So I'm creating a list of it. Well, a list of numbers is just a vector, okay. So now I want to do dx by dt and dy by dt together, kind of thing. So I'm doing dx vector by dt. Okay, notice that this x with a line underneath it is not the same as this dx here without a line underneath it. This is a scalar, this is a vector, which is describing all my variables put together. This is just notation. This is kind of where notation in ODEs, I get frustrated with it because I could come up with such a better job, I think. But then you try and make it clear and you actually end up, for some people, making it less clear because you're not, because basically what you're trying to do is show that these two things are related. That's why you use an x vector rather than say u vector or v vector, which comes on to something else. Okay, I then also want to create a, let's say, a table of all my coefficients. So I'll have a in one row and b in another row because this is like one equation. So I'm going to put that in one row, and then I'm going to put my coefficients of this equation in the other row. So c, d, and showing that it still lines up. So this is x, this is y, but this is now dx by dt, and this is dy by dt. You're happy that, you know, I've just formed them as a table like that. Well, a table is just a matrix. Yeah, so I'm going to call that matrix A. Okay, so this is just a matrix which I've created. This is the list which I've created. And then the same thing I can do with, if I just list my constants at the end. So I've got k1 and k2. Well, that's just another vector. I'm going to call that one for k. Okay, so now when I put these two things together, these two equations together, I can write it in vector matrix notation, or just matrix notation, if you consider a vector as just a special case of a matrix. All right, so I'm basically trying to combine these two equations into one equation. And the way that I can do that, so if I multiply a, my coefficients, by my variables, which is x, and then I'll just have some tag-alongs, you know, my constants hanging around at the end. Now, I'm just going to expand this out just to show you that it is, that I do get these two things back again. You can fast forward the video if you want to, but I really suggest you hang around, because this is kind of, if you get the basics done, if you know, you can build on these strong foundations rather than thinking, oh my word, what does that mean later on down the line. So I've got dx by dt. Well, dx, my x vector, is just xy, okay, by dt. And that's going to be equal to my coefficient matrix. I'm just making substitutions now for exactly what each thing is. So my coefficient matrix, my vector here, xy. Notice that I'm writing it now as a column vector. The reason for that, if you think back to linear maths, I'm going to end up multiplying by a matrix by a vector. Okay, so essentially a matrix by my matrix, if you consider a vector as a 2 by 1 matrix or 1 by 2 matrix. Okay, so when you multiply matrices together, so say if you have an m by n matrix, so m columns and m rows and n columns, okay, and I want to multiply that by a p by q matrix, okay, n by q matrix, these two inner numbers have to match in order to be able to multiply them, and the dimensions given by the outer two numbers. Read back on your notes from linear maths in the first year, those are the days, if you're unsure of that. And then I'm going to end up with my constants again, so I'm going to write k1 and k2 like this, just a small note. All right, so now I'm going to try and expand these two things out. So actually, what I'm going to do is I'm going to expand them out in a special way. All right, so I'm just going to consider the first element and like the first row. So like, yes, the first element of each vector and the first row of each matrix. right? Because that should correspond to my first equation, and likewise the second element of each vector and second row of each matrix should correspond to my second equation. So let's verify. So I basically should end up with dx by dt, so considering the first element of this vector here, should be equal to a, considering the first row, so a times x plus b times y plus the first element of this vector, which is k1. That's looking good. That looks like the first equation which I've got up here. All right. Now let's consider dy by dt. Okay, that should be equal to c times x, the second row now I'm considering the second elements, the second row, so cx plus dy, good, plus my second element of this vector here, so k2. That's good. Okay, so I've got it back out again. So in other words, it works. Big tick. Cool. So basically, now I can just consider these two equations combined looking like this. And obviously, you should be able to see that if you have n different variables, you just have an n-dimensional vector here and an n by n matrix here, and then just n coefficients on here. Okay, so now what I can do is, once I've done all that, I'll just write this out again. So I've got dx by dt now, dx vector by dt, is going to be equal to ax plus k. Okay, so that's now what I want to consider. This is now my linear system combined into one equation, okay, which is so much easier to work with, All right, okay, so now I want to consider these things called equilibrium points or critical points. Now, if you remember back to A-level, way back to A-level, say if we have a function, let's call it y equals, I don't know, 4x squared minus 2x, all right? Well, if you wanted to find the stationary point of this function, so when you graph this function, it's going to look something like this. If you want to find the stationary point, sometimes known as the equilibrium point or the critical point or something like this, in actual fact, in this course, we're going to call it either the equilibrium point or the critical point because it sounds more grown up rather than stationary point, because stationary point is kind of too obvious. Yeah? It's called an equilibrium point, but it's exactly the same thing. It's just basically where the function changes. Actually, the reason why we call it equilibrium point will come clear when we do phase portraits, because that kind of has a more applicable meaning there, but equilibrium, stationary, whatever. So the stationary point just corresponds to the maximum or minimum value. So in other words, here. And that's going to be where the gradient is equal to 0. All right, well, we can write the gradient down as dy by dx. Okay, and the stationary point is going to occur when the dy by dx is going to be set equal to 0. So let's differentiate this. So perhaps we should differentiate this first, shouldn't we? So dy by dx, it's just A-level stuff. So what's this? It should be 8x minus 2. Okay, so when we set it equal to 0, we get 8x minus 2 equals 0, yeah, which implies that our x-coordinate is going to be at, what's that, quarter? Yep, okay, so our x-coordinate is going to be a quarter. Okay, and then we can plug this back in and find out what the y-coordinate is, etc., etc., etc. We're going to do pretty much exactly the same thing now, just with this thing which we just worked out up here, this dx by dt equals ax plus k. Okay, we're going to do exactly the same thing. So we can get our equilibrium point now. Equilibrium point, stationary point, same thing. So we're going to set it equal to 0. So in other words, we're going to get this right-hand side equals 0. Equals 0, okay, and then that implies that if we basically just want x on its own, so let's move the k over the other side. Ax equals negative k. Okay, all very well and good. Now we want the x on its own, so we're going to have to almost divide by this matrix. Remember that we can't really divide by matrix. Okay, we can't divide by matrices, but we can introduce this idea of the inverse of a matrix. Because if you like, if you have 5x, okay, equals 2, yeah. If you want to then take, or even this case here where we had 8x equals 2, yeah. We took the 2 over the other side, which is exactly what we've done here. But then we divided by 8. Well, the other way of thinking about that is multiplying by the inverse of 8, or the multiplicative inverse of 8. And of course, the multiplicative inverse of 8 is 8 to the minus 1, okay, which is 1 over 8. So that's effectively what we're multiplying by, the inverse of 8 here, and multiplying by the inverse of 8 on both sides. So if you multiply by the inverse of a on both sides, we get this. This is just, again, it's just a reminder, but it's been, 2 years since you've done linear maths, if not longer. So this is just a reminder. And remember that an inverse multiplied by your number, it's a bit like doing, so here, 8 inverse multiplied by 8. Well, 8 inverse is just 1 over 8 times 8. So that's just going to be 1. Okay, and the matrix equivalent of 1 is the identity matrix. Okay, so we can pretty much just get rid of this and just get this. So our x vector at the equilibrium point is given by this. Now, to kind of show that it's at an equilibrium point, we can write it as this little subscript e. Okay, and of course x vector is xy. Okay, well, if it's subscript e, then we put subscript e on all other elements. Okay, so this is how we can describe. We've now got an expression for the equilibrium point. Okay, so there we go. So maybe I could just put that there. Same thing. All right. So okay. Now, what happens if we're at the equilibrium point? What happens if our equilibrium point is at the origin? Okay. Well, are you happy that our constants are just going to go to 0? All right, because we've got a linear function. We've got a linear function. So we've got, what is it? Where are we? Ax plus by plus k1. Okay. Well, we can rearrange that to get it in the form of y equals mx plus c. Okay, and this is going to be our constant, effectively k1. All right. I mean, it may not be k1 exactly. It may be k1, say, like over, what was it? Over b. Yeah, because then we want to get y on its own, so it would be k1 over b. But effectively, we've got c on its own, and that corresponds to the y-intercept. All right. Well, the y-intercept, so the linear graph is going to look like this. Okay, and that's k1. Just for the purposes of this explanation, just take k1 to be that, or b to be 1. That's what I'm basically saying there. So this is the y-intercept, all right? Well, if we're going through the origin, so in other words, if we're going through the origin, so our equilibrium point is xe, right, 0, 0, then there's no y-intercept, so our k1 effectively just equals 0. Yeah? So basically, if we're going through the origin, that just means that our k vector disappears. Okay? And so we're just left, if we're going through the origin, we're just left with dx by dt as being ax. All right? So that's if we're going through the origin. If our equilibrium point is going through the origin, okay, then we get this. What happens if our equilibrium point isn't going through the origin, though? So in other words, let me just graph it out again. Just graph it out. So let's say that our equilibrium point is over here somewhere. And so this is just our equilibrium point, xy. All right. And it has x component xe and our y component ye. Yep. And so what happens if we're over here? Well, we can move this equilibrium point to be at the origin if we move the whole function. So we apply some transformation to move this point over here to the origin. And we can do that by moving it to the left or to the right, whatever. But basically, we're going to have to move it by what? We're going to have to move it by xe. We're going to have to move it by this distance here, which is just xe. And we're also then going to have to move it down. Going to have to move it down by what? Well, that distance there is just ye. Okay? So in other words, if we move it by... so we're moving our point x now, our equilibrium point x. Maybe if I write it out in... maybe if I write it out in proper vector notation. So we've got xy, our point xy over here, which is our equilibrium point. We're moving it to the left by xe, or to, horizontally by xe, and we're moving it up or down by what? By ye. Yeah, are you with me so far? If you just visualise this picture, hopefully you can see it. So this is x, this is y. Hopefully you can see it. Okay, well that's just the same as saying this is our vector x, and this is our equilibrium point, xe. Okay, and I'm going to call that transformation, x tilde. Okay, so x tilde in other words, so I'm moving it to the equilibrium point. Maybe another way of writing it out is, if you're not quite seeing that, x minus xe, and then y minus ye. Okay, so we're moving our x coordinate to the left by xe. We're taking xe away from our x coordinate, or adding it if it was over here, say, or whatever, and y we're taking away ye. All right, and so that's what x tilde is. So we've now got an expression for x tilde. So we can basically move wherever our equilibrium point is. We can move it to the origin always. So we can basically always get this situation. But just to show that we can always get this situation, let's just change our notation. Instead of being x, because this is a specific case when our equilibrium point was at the equilibrium, our equilibrium point was at the origin. Now we're considering the case when it's not at the origin, but we can move it. So just to kind of take into account of all cases, we're going to denote everything by x tilde. So equals ax tilde. And that's fine. Okay, so this is the general kind of form, always for a linear function. So we don't even have to worry about the k, the constants vectors hanging around at the end. Okay, and that's virtually what I want to leave it. So basically what I've managed to do is I've taken my system of linear equations, which is up here, okay, autonomous linear equations, all right, and I managed to convert it into this, into one neat little equation. And then in future videos, now we've got this, in future videos we're going to see exactly what we can do